Hey everyone, in this video we're going to continue on to the lesson that we did in class. We're just going to keep following up with linear modeling. So in this first question we have, a warehouse is keeping track of its inventory of cardboard boxes. At the beginning of the month they had a supply of 1,275 boxes left. They use boxes at a rate of 75 per day. So how many are left after 10 days? Well, we can either set up an equation here or we could just think about this for a second. So each day we know that they're going through 75. So there's 10 total days. So within those 10 days, they went through 750 boxes. Now, if we started at 1,275, we're going to subtract the 750 that we had here. And when we plug that into our calculator, we're going to get 525. Okay, so now what we're going to do is write a linear equation that models exactly what we just did. So we're saying that number of boxes is n left after d days. So this is a function in terms of days. So we know that the boxes is something that we are trying to compare. So that's going to be our output value, right? That's our y. So that's n equals. Now it's going to be a little bit different here. So you could set it up two different ways. So we could take this 1,275 and we're going to subtract 75 per day. Okay, so we could write it like this. Or if you prefer, you can keep it the way we kind of always have it. It's a negative 75 d plus 1,275. But we know that our rate is negative because we're getting rid of some, or like running out of them. So that's got to be a negative sign in front of that 75. Now, if the warehouse needs to order more boxes when their supply reaches 150, how many days can they wait? So we're worried about when the supply reaches 150 boxes. So we're going to plug that in to n. And when we're looking like something like this, now we're just solving for d the same way we've been doing. So we're going to take that 150 and we're going to subtract 1,275 from both sides. And we end up with negative 1,125 equal to a negative 75 d. I'm going to divide both sides by the negative 75. And so we end up with n equal to 15 days. I'm sorry, d equal to 15 days. If after 5 days they start using boxes at a rate of 90 per day, how many days will it be before they run out of boxes? Show your work. So let's think about this first piece. So after 5 days. So 5 days, they're still doing the normal rate of 75. So 5 times 75. And that's going to equal 375. So that's 375 that will be gone in this case. So I'm going to take the original that we started with, 1,275, subtract 375 from that. We get 900. Now, if I rewrite my formula, I'm thinking it's now going to be n is equal to negative 90 plus 900. And we're just going to figure out we want to figure out how many it takes for us to run out. So if we run out, we'd be at 0. Now I'd subtract the 900 from both sides. It's going to be equal to 90D. I'm just going to shrink this a little bit so I can fit a little bit more. But in this case, I'm going to divide the negative 90 from both sides. And we get 10 equal to D. But don't forget, this was after we already allowed 5 days to pass, right? That's 75. So 10 plus 5 is 15 days. That's how much we would run out completely. Okay, let's look at the next question. In exercise 2, the cost C in dollars running a particular factory that produces widgets, W, can be modeled by the linear function below. C of W equals 1.25 W plus 2,175. Okay, how do you interpret the fact that C of 100 is equal to 2,300? So basically, let's think about it. We've talked about functions before this unit. So we're thinking about W here. We're plugging in W. So that's our input. And the input's widgets, excuse me. So for every 100 widgets, now let's think the output is what we would get as an answer here. So the cost of running the factory is 2,300, right? Because the cost C in dollars running a particular factory that produces W widgets can be modeled by the linear function. So W is my input of widgets. For every 100 widgets, the cost of the factory running is 2,300. Now, given a physical interpretation of the two parameters of the equation, so the first part, the 1.25, looking where it is, that's our slope, right? So the slope is like the average rate of change, how much it's going to increase every time. So the 1.25 means for every additional widget, the cost of running the factory increases by $1.25. So for every additional widget, the cost of running the factory increases by $1.25. Now the second part, that's our y-intercept. That's our initial. So remember, that starts when we're starting at 0, plugging in as our input. So when 0 widgets are made, running the factory costs $2,175. Okay, so we're just thinking about what the slope and the y-intercept mean in terms of context. So biologists estimate that the number of deer in Rhode Island in 2003 was 1,208, and in 2008 it had grown to 1,488. Biologists would like to model the deer population P as a function of years T since 2000. Represent the information we have been told as 2 coordinate points. Be careful to know what your values of time are for each year. So when I go to set this up, we want 2 coordinates. Be careful with time though. So our first one here was 2003. We'd have 1,208. Well, I'm not going to put 2003 in. We're talking about the years since 2000. So 2001, 2002, 2003, it's been 3 years since. So that was a population of 1,208. Same idea for the year 2008. It had grown to 1,488. So years since 2000, that would be 8. And then we'd have 1,488. Now we can calculate the average rate of change here, right? The slope, include the proper units in your answer. So remember, change in y over the change in x as long as you're consistent. So in this case, when I take 1,488 subtracted by 1,208, we end up with 280 divided by 5, which is 56. So when we think about what we found here, it's when I go to explain this, it's 56 more deer per year since 2000. Okay, 56 more deer per year for their population since 2000. And I kind of said that in part B already for C when it says given an interpretation of the value found in part B. Well, if I go to do that, it's going to say that each year since 2000, the deer population of Rhode Island increases by 56. And you can say 56 deer if you'd like. But each year since 2000, the deer population of Rhode Island increases by 56 deer. So we're just careful to include the context in that as we go. Now, if I want to determine a linear relationship between the deer population and the year since 2000, T, we can, because we already figured out the slope. Right, that's what part B got us, that was our slope. Now we also want to figure out what 2000s would have been at that same rate. So right now, I know P is the output equal to 56 T, but we got to figure out what my y-intercept would be. So if I think about this, to make this all check out, I could just find my y-intercept by plugging in another value, right? I could plug in either one of these two. So I'm going to borrow this 2003 here, that 1,208. So we had 1,000. 208 equal to 56 times 3 plus b, so we can solve for b. So when I do that, 56 times 3, that's 168. And when I subtract both sides by that 168, we get 1,040 is equal to b. So that's what I'm going to plug in here, 1,040. So here is my equation. The population is equal to 56t plus 1,040. Right, because we know both points would have worked out there. So I could have done the other point, 8 and 1,488 would have worked the same way and still got me the 1,040. Now, how many deer does this model predict were in Rhode Island in the year 2000? What does this represent in the linear function? So in 2000, we decided, remember, it was 1,040. Okay, this is our y-intercept. Okay, because 1,004 deer in 2000, and that's where we started. So that was like our 0 that we're plugging in. So that was our y-intercept. How many deer does the model predict in Rhode Island right now? So we're just plugging into our formula, right? P is equal to 56 plus 1,040, but notice I left that blank. So this is the year 2020. So since 2000, it's been 20 years. So according to our model, if I just plug that in, 56 times 20, we'll get 1,120 plus that 1,040. So right now we predict that there are 2,160 deer in Rhode Island right now, based off this model. Is that true? Maybe not. Maybe they've had to make adjustments to this model since then, but that was what we're predicting based off that model. Okay, last one. Water is draining out of a bathtub such that the volume still left, G gallons, is shown as a function of the number of minutes, M, it has been draining. Calculate the average rate of change of G over the interval 0 to T to 2. So in this case, when I'm looking at that, remember your average rate of change, we need your 2 points. So the interval represents X, so we'd have 0. And at 0, we'd have 62. And then we stop at 2, where we had 28. So average rate of change, we take the Y, so 28 subtract 62 over 2 subtract 0. So when I have 28 subtract 62, I end up with a negative 34 over 2, and we get negative 17. And remember, when we talk about it as units, it's negative 17 gallons per minute. Now we'll do this again here for the next one, but this time we're doing the interval from 2 to 4. So 2 is still at 28 gallons, but for 4 minutes, we'd be at 12. So average rate change, 12 subtract 28 over 4 subtract 2. In this case, we'd end up with, when we do 12 subtract 28, we should end up with a negative 16 over 2. We get negative 8. So it's saying negative 8 gallons per minute. And now remember what those negatives mean. That means that's the rate that it's decreasing, right? Because we know we're draining the bathtub. So if the bathtub's being drained, those should both be negative because they're losing the amount of gallons of water. But we cannot say this is a linear relationship. We can't say it because the two average rates of change are not the same. Okay, remember that the average rate of change And anything that's linear is going to be the same. That slope is going to be a constant rate that it's decreasing by. If these two aren't decreasing by the same amount, this is not representing a linear amount. So if you have something that values, if we can't get a slope that works for all of them, this isn't linear. Okay. So tomorrow in class, we're going to do more practice. Hopefully this video helped feel like we understood some of our modeling, but we'll practice more tomorrow. Thanks for watching.